All right, we're going to start looking at lesson 16, which is maximum and minimum values. This is where we're starting to get into the beginning parts of doing the calculus to solve problems about optimization, which is like the optimal or best way of doing something. So some examples are in this overview here. What shape of the can will minimize manufacturing costs? Or what's the maximum acceleration of the spacecraft? What angle should the freeway off ramp be inclined to make to minimize tire slipping? So, all kinds of applications out in the real world have to do with finding maximum or minimum values where a function is either its highest or its lowest point. And so we're going to start this process. It'll take us a couple of lessons to kind of get all the way to the end of that process and actually solve those problems. But in this lesson, we're going to start by making the definitions of what those kinds of things are and looking at where what x values they might occur at. So let's start with a set of definitions. We are going to be talking about C being a number in the domain D. We'll call the domain the whole domain D of a function f. Then f of C is an absolute maximum, which we sometimes call a global maximum of f on D if f of C is greater than or equal to f of x for all x in D. So that's saying that this y value, this f of c y value, is bigger than or at least equal to every single other y value, all x. So that's why it's called an absolute or a global max. Similarly, a global min would be the same thing. It's just that f of c, that y value, would now be less than or equal to f of x, all the other y values for all x in the domain. Okay. So those are absolute or global. We use those two words interchangeably. I will probably use them interchangeably. But then we also have another option, which is what we call a relative or local max. And so that has the same quality. The y value f of c is going to be greater than or equal to f of x. But now we're no longer requiring it to be that way for every single x in the domain, but just on some interval. There's some interval, we'll call it AB, that contains C. So on both sides, C is not the endpoint of the interval. On both sides of C, that x value, there's a little neighborhood there where its y value is the biggest on the block, so to speak. And same idea for a local or relative min. It's just now that y value is less than or equal to all of the other y values in its neighborhood. So on some interval AB that contains C. So maximum and minimums, we can have it global or we can have a local. The one thing that's really, really critical to realize is that we're always talking about, so first of all, let me just point this out. We're talking about this word extrema. So we have absolute extrema, which would be absolute maxes and mins, or local extrema, which are relative maxes and mins. But every single one of those that we're talking about is a y value. So it's really important to note that extrema, which is kind of the plural for extreme values, are always y values. Okay, they're outputs. Go back and read these definitions. They're all f of c is greater than f of x. It has to do with the y value being the biggest y value or the y value being the smallest y value. So The x value, we are going to be interested in x values at these points, but it's important to realize that the x values are locations, markers, where the extrema occur. Okay. So we're always talking about y values when we're talking about maxes and mins, always. Okay, so I have some examples here on the next page. I would like you to look at these 4 different pictures and look at the definitions of what we just did, how we defined relative and global extrema. And I want you to go ahead and write down whether there's any local or any absolute extrema for each of the 4 functions. So press pause on your video while you try this. I'm going to just have the answers kind of pop up. So now is a good time to press pause and give it a try. Okay, so I have filled in some answers here. Let's take a quick peek at each one of these functions. We'll start with this function here on the left side in green. So I see that I have this filled in dot. I trace this around. I've got an open dot on the end. So I definitely have this y value. This point is the lowest point of the whole graph. So it's -3 is a global minimum. But I also see that here I have a low point. I have a point where in the neighborhood anyways, on either side of it, it is the lowest y value in the area. So that means that 2 is a local minimum. I'm sorry, that's this one. The 1 is a local minimum because it's the y value. The y value is the 1. Okay. And then we have one more local min right here. The function kind of dips down, and in the neighborhood, this is the smallest y value, and that y value is 2. So 2 is also a local min. I don't have any maxes because both of the places, the candidates that would be sort of the top in the area anyways, are open circles. So they're not actually points on the graph. Next, we have the graph in orange, and if I'm following, it looks like it goes on forever in this direction, and since it's kind of indicating that it's going down, we cannot claim that there is a global min anywhere, because we would have to sort of assume this is forever decreasing. But we do have a local minimum right here in the area. This is the lowest y value, and that y value is -2. And it looks like I have a local max here at the top of this cusp. Again, in that area, it's the highest y value. So that's y value is 3. So we have a local max. And up here it does, since this ends, this is where my function ends, and it's going down forever in this direction, that would be the tallest y value this function will ever attain. So it is a global max. On an endpoint, we generally, the way our definition is structured, we could not call it a local max because it does not have an interval that contains this c value. I mean, this is happening at x equals 5, and I don't have any y values on the other side of that, so I couldn't say there was an open interval where it's the highest. So therefore, we don't call it a local max. It is a technicality. Some calculus books will call it a local max because they allow endpoints to be just sort of one-sided intervals. But we're going to go with the definition that we have from our textbook. So it's going to be that it's not a local max because of the fact that there is not an open interval around it. It's not a two-sided neighborhood there. Again, we don't have a max, I'm sorry, local min at this dot because it's not filled in, so it's not a function value. Okay, moving on to the function in the blue. It goes down forever, is indicated here, so there's definitely no global min, and there's no global max because that top value is not filled in. So without it being a filled in circle, I can't have it be a maximum value. And then there are no places in between this function. It's constantly increasing. So everywhere you go, there is going to be there's not going to be any tallest or lowest points in the neighborhood. So there are actually no extrema for this particular function. And then last but not least, in contrast to that, if I have this constant function, by the way our definitions are phrased, it is all four of them. It is a local max, it is a global max, it is a local min, and it is a global min, because it is both greater than or equal to and less than or equal to every other y value in a neighborhood or for the whole domain. So one last thing we will cover in this video is looking at how will we know, since our above examples kind of showed us that, well, you can have maxes and mins or neither or only some, and how will we know that you absolutely have? How can we guarantee that it has at least absolute extrema? Not necessarily talking about local relative extrema, but I can guarantee you that you'll have absolute extrema by the following theorem. The extreme value theorem tells us that if y equals f of x is a continuous function function, there we go, on a closed interval. A to B. If those two things are happening, then we can guarantee f attains both an absolute max and an absolute min. On that interval A to B. So the two requirements we have is that the function is continuous and it's continuous on a closed interval. And then that guarantees that in fact you will have both a max and a min on that interval. Just like the intermediate value theorem, it doesn't tell you where specifically, like which x value it happens at. We just know that there will be an x value somewhere in there that attains a max at that value, and an x value somewhere in that interval that it'll attain a min. So I actually would encourage you to then look at these past examples and look at this Desmos animation, because the next thing we're going to do in the next video is start talking about the types of points where we could find these extrema and those examples. And this demonstration, this animation will help you figure out some candidates for where the extrema can occur.